Welcome back, anatomy students. This is the second chunk of our neuron presentation. This is about action potentials. So now that we know about the different characteristics of neurons and we understand what a membrane potential is, now we can talk about how these local potentials are going to come together and spread throughout one neuron and then move on to another. So here we're going to be talking about action potentials. A synonym for action potentials is a nerve impulse. The graph that you see here is showing us the changes that occur in the membrane potential of a neuron as a nerve impulse progresses through a small area of the cell membrane. And remember that membrane potential is simply a measurement or the difference between the charge of the extracellular fluid and the charge of the intracellular fluid. At rest, our membrane potential is at a negative 70 millivolts, and that's what you see at the very beginning of our graph here. But then as time moves on, you can see that that's all going to change. So you're going to see this graph again. All right, here are our objectives. So after listening here, you should be able to explain the role of local potentials in the propagation of an action potential. You should be able to describe how an action potential is produced, define a refractory period, and differentiate between the absolute and relative refractory periods. And then number 4, describe saltatory conduction and how it affects action potential propagation. All right, so the membrane potential of a neuron that is conducting an impulse is going to give us something called an action potential. So an action potential is just the changes in charge between the extracellular fluid and the intracellular fluid in a neuron that is active, that is actually conducting an impulse. So our neurons are going to start at rest. And when the neuron is at rest, it's kind of like a salty banana. And I know that those of you that have taken AP Psych probably know what that means. For those of you who haven't, here's what it means. First of all, you need to know a couple things. Number 1, that salt, like table salt, has sodium in it. And number 2, you should know that bananas are very rich in potassium. And so our neuron is like a salty banana. You've got potassium on the inside and you have sodium on the outside, just like if you took your salt shaker and poured salt on your banana. So just remember that a resting neuron is like a salty banana. Now, the term resting just really bothers me because it makes you think that the neuron is peaceful, that it's stable, but it's not. The resting potential is an unstable configuration, and that's what we want. Remember what I said about a river that's got a dam in it and all of the water backs up so that when the channels in that dam open, the water just flows out. That is what we want. We want that flow, that influx of ions to come into the cell when the channels open, because that's how we get an instantaneous response. If we had to wait a couple of beats in order to respond to something, we could really sustain some serious tissue damage if that's the scenario that's going on. Like touching a hot stove or something. We don't want to leave our hand there for a while until we decide what to do. We want to figure that out right away. So this idea of having a resting neuron is a little bit contradictory to me, because I feel like if you're resting, then all is well, you're stable, but not in neurons. If that neuron is resting, it is ready to change. So it's an unstable configuration. Okay, so when at the input zone receives a stimulus, the very first channels that are going to be stimulated to open are the stimulus-gated sodium channels. And so remember that stimulus-gated sodium channels are also called ligand-gated channels. And so this is where they bind to a molecule like a neurotransmitter, and that molecule is going to cause them to open up. So when a neurotransmitter binds to these receptors, they're going to open and allow sodium to flow into the cell. Now, Not all of the sodium channels are stimulus gated, though. Some of them are voltage gated, which I'll get to in just a second. But here's the thing. Enough of these stimulus gated channels have to open, and enough sodium has to flow into the cell to raise that resting membrane potential from -70 to about a -59. Now, there are some sources that say that that's -55. I've seen -60. So it's got to be like right in that area, but threshold has to be reached. If threshold is not reached, then that possible action potential is going to die out. It's going to dissipate and it's not going to go anywhere. But if enough sodium flows in to raise -70 up to about a -59, then that's going to cause our voltage gated sodium channels to open, and then that's going to allow for more sodium to rush in, which I'll get to on the next slide. So if you take a look at our picture that we have at the bottom, this is our salty banana. This is our resting neuron. You've got more sodium, the pink circles that are on the outside in the extracellular fluid, and you've got more potassium on the inside or the intracellular fluid. And as you can see on our voltage meter, we have our little trace right here at about -70. This is resting. And remember that the negative is telling us that the inside of our cell has a negative charge. And so this electrode is measuring the intracellular fluid while the other one is measuring the extracellular fluid. And then the difference between that is where that number 70 actually comes in. Okay, so now we've got sodium rushing in, right? So let's just say that enough of our stimulus-gated channels were open, enough sodium has rushed into the cell in order to raise our membrane potential to a -59 millivolts, and now threshold has been reached, and so now that's going to cause other voltage-gated channels in the vicinity to open up as well, and more sodium is going to rush in, and that's going to cause more voltage-gated channels in like a larger radius to open up, and more sodium rushes in. So what we've got here, folks, is a positive feedback scenario, right? So the more sodium that comes in, the more voltage gated channels are going to open up, and that's going to allow even more sodium to come in, and so it's just going to go up, 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 and that's exactly what you see here. This is depolarization. We are depolarizing the cell. Remember what I said in the last video, that when the cell is at rest, the cell is polarized. You have more positive charge outside than you do inside. Well, by opening up our sodium-gated channels, now you're equalizing that. You're bringing more sodium in. You're making the inside of the cell more positive, like the outside of the cell. So that's depolarization. You're removing the separation of charge, and that is what's happening here. It's going up. It's becoming more positive. It's moving more towards zero, and it's going to keep going up, up, up until it reaches a +30 millivolts. And at +30 millivolts, those the voltage-gated sodium channels are going to close. The voltage-gated sodium channels are kind of on a timer. They're only going to be open for 1 millisecond, and then that's it. They close. And what that means is that the peak of your action potential on the graph is not going to go above +30. It can't, because you're going to close those sodium channels, and then that's it. Like the inside of the cell is not going to receive any more sodium, and so it's not going to increase its charge above a +30. So what that means is that all action potentials are going to have the same magnitude. They're going to have the same height. Now, here's an interesting thing about our potassium channels. Potassium channels are going to be stimulated to open at the same time as the sodium channels, but they don't. They are slow to respond. So even though they're stimulated to open at the same time as sodium, they are not going to be open until +30 millivolts is reached. It just takes them a little bit more time to open up. Let's just think about the doors that you have at your home, right? Most of us have a front door, and most of us have a garage door. And our garage door is maybe on a garage door opener. Well, if you want to open and close your front door, you just open it, close it, open it, close it. It's very quick, easy. It opens right away because you're pushing on it, you're putting force on it. The front door to your home is like the sodium channels. They open, close very quickly. But your garage door that is on maybe a garage door opener, that's going to open up very, very slowly. And it's even going to close very, very slowly. And that's how the potassium channels are. So they're going to be stimulated, like the button, like the button on your garage door opener is going to be pressed, but it's like the door doesn't respond right away. It's got to wait a little while before it'll actually start to open. And so that's what happens with our potassium channels. They're slow to respond. Whoops. It wasn't plugged in all the way. So they're slow to respond. But by the time our action potential reaches plus 30 millivolts, by the time the inside of the cell has a charge of positive 30, now our sodium channels, they snap shut, and our potassium channels have now opened. And now we get potassium rushing out of the cell. Why does potassium rush out of the cell? Here's why. Because like charges repel. Now that we've got all of this positive sodium inside, and the sodium channels are closed, so now the sodium can't escape, the potassium is like, get me out of here. There's too much positivity in here. So they want to leave. Like charges repel. So now that the potassium channel doors are open, the potassium can now flow out of the cell. And when the positive potassium flows out, well, you've got positive charge that's leaving the cell. And so now the inside of the cell is going to become more negative. You are going to re-separate the charges. This is a phase called repolarization. And as you can see on our voltmeter picture, you have repolarization happening, and you've got a downward slope to our action potential graph. Now, our potassium channels, like I said, like they're starting to close here, but they're still open. And so our potassium has more time to leave the cell. And that means that like too much potassium is going to rush out of the cell. And that's going to put us into another phase called hyperpolarization. It's going to cause the charge on the inside of our cell to go below resting, to go below negative 70. And that is going to cause another phase. All right, we will get there in just a moment. But for now, let's just review all of the things that we've already talked about. So at the beginning of our graph, here at negative 70, this is our resting membrane potential. Here at negative 70, our cell is polarized. You have separation of charge. But here we get a stimulus. And this could be in the form of a neurotransmitter, for example, because remember, the very first channels that are going to open are the stimulus-gated, also known as the ligand-gated sodium channels. So some neurotransmitter is going to come along, bind to a couple of receptors in the input zone of our neuron, and it's going to cause these channels to open. If enough channels open and enough sodium flows in to raise our resting potential to about a negative 59 millivolts, then in the area surrounding these ligand-gated sodium channels, you're going to have voltage-gated sodium channels open, and sodium is going to rush in, and that's going to cause a positive feedback event where more sodium comes in. You get an increase in our membrane potential. This is a phase called depolarization because you are de-separating the charge, and the inside of our cell is becoming more positive. And as the inside becomes more positive, more voltage channels are going to open and more sodium is going to flow in until 1 millisecond goes by. After 1 millisecond goes by, as you can see, down here at the bottom, as 1 millisecond goes by, Those sodium channels are now going to close, and usually by that time we are at about a positive 30 millivolts. Remember that our potassium channels were stimulated to open at the same time as our sodium voltage gated channels, but they were slow to open. But by the time we get up to positive 30 millivolts, our potassium channels are open. And now what happens is that our positively charged potassium ions are repelled by all of the positive sodium ions that are inside of the cell, and they get out of that cell. So now they're going to rush out of the cell, and when the cytoplasm of the cell loses all of this positively charged stuff, that's going to cause our membrane potential to become more negative. We have a re-separation of charge. This downward slope is called repolarization. Now, during this time, during repolarization, our potassium ion channels have started to close. But just as they open slowly, they close slowly too. Just think of your garage door. And so you're going to have more and more potassium ions leaving the cell. That's going to cause our membrane potential to dip below negative 70, to dip below resting potential. And that is going to put us into a phase called hyperpolarization. And our voltage-gated potassium channels aren't going to close until a total of 2 milliseconds from the time of the stimulus occurs. So this hyperpolarization is going to put us into a period that's called a refractory period. This means that the local area of the membrane is not going to be able to be restimulated. This is going to happen for about half of a millisecond, and no action potential is possible. Regardless of how strong that stimulus is, that area of the cell membrane will not be able to generate an action potential. After about half a millisecond, it's going to enter into a second refractory period called the relative refractory period. During this time, only very strong stimuli can give us an action potential. Now, when I say very strong stimuli, there's something that you have to remember. The size or the magnitude of these action potentials never changes. It's always going to have a height of about a positive 30 millivolts. So when you have a very strong potential, remember we have this positive feedback event that's happening. So the more sodium voltage channels that are opening because of these stimuli, the more sodium is going to flow in and generate more action potentials in more areas around the initial area that received the stimulus. Very strong stimuli are going to create action potentials at a higher frequency. So you can see that on our graph here. Notice that the height of the action potentials hasn't changed, but the number of them have. And notice that they are very, very close together. And so they're just happening at higher and higher frequencies. So remember that it's not the magnitude of the action potential that affects the strength of affects the strength of a response. It's going to be the frequency, how many action potentials there are in a given amount of time. That's what's going to determine how strong an actual stimulus is. So the higher the frequency, the stronger the stimulus, and that's all because of this positive feedback effect that happens when sodium starts flowing into the voltage-gated sodium channels. So how does this occur down an axon? Well, it's kind of like a domino effect or like a chain reaction, right? If you set up a bunch of dominoes all in a row and then like you just flick the first one that you put down, they kind of all fall down in succession. That is what's happening down the membrane of an ion. So if we take a look at picture number 1, over on the right-hand side of your slide, depolarization during the action potential will cause more adjacent voltage-gated sodium ion channels to open. So once this area that's highlighted in yellow depolarizes, the influx of sodium is going to cause adjacent sections, as in picture number 2, to depolarize. And then as more sodium flows in, that's going to cause another adjacent section. So it's just kind of in chunks, like a chain reaction. That's how it's going to occur. Now, the thing to know about action potentials is that they are never going to flow backwards. So they're never going to go from the synaptic terminal or the axon terminal backward toward the cell soma. They're always going to flow in one direction. They are unidirectional. And the reason why is because if we take a look at picture 2, when picture 2 is depolarizing, the section in picture 1 is in their refractory period. And remember what I said about the absolute refractory period? You can't receive a stimulus. And this stimulus, it's not growing. And so even if section number 1 is in a relative refractory period, it's not going to be able to stimulate that to generate more action potentials. So it's never going to travel backwards. The other thing that I wanted to mention about action potentials is that unlike local potentials, action potentials are all or nothing. And so if you have enough local potentials added together to reach threshold, you're going to get an action potential. There's no ands, ifs, or buts about it. You're going to get an action potential. So if threshold is reached, action potential happens, all or nothing. If threshold is not reached, nothing happens. That's where the nothing part comes in. So action potentials are all or nothing, and they do not flow backwards. All right, so axons that are covered with a myelin sheath are going to propagate nerve impulses faster than unmyelinated neurons. And I may as well interject here that also the diameter of the axon matters. So axons that have a larger diameter are going to propagate nerve impulses faster than axons that have a smaller diameter. But what we're looking at on the slide here is something called saltatory conduction. The roots for saltatory is Latin saltare, and that means to jump or to leap. And essentially that is exactly what's happening in a myelinated neuron. So this is the myelin sheath along a neuron, and you can see that it's not continuous, right? We have these tiny little gaps here in between the different sections of myelin along the axon. These gaps here are called the nodes of Ranvier. And it is only here in the nodes of Ranvier where you are able to get an influx of sodium and depolarization, and you're actually going to get the action potentials occurring. They do not happen in the parts of the axon that are surrounded by the myelin sheath. And so they're going to move very, very quickly underneath the myelin sheath. And so instead of having to have, like back on this picture, instead of having to have every single section having to depolarize and repolarize and go through the refractory period, now that's going to happen faster because it's only happening in the nodes of Ranvier. And so if we start with an action potential here in picture 1 on the left-hand side, that those ions, like in this local area, are going to switch. The sodium will flow in and the potassium will flow out, but then that potential is going to carry through the axon underneath that myelin sheath, and then this next node is going to go through the whole cycle, and then that gets carried on if you look down here at picture 2, and then the next node. So it's really only the parts that are exposed, the parts that are not surrounded by the myelin sheath, that have to go through the cycle, and that's going to make conduction of the nerve impulse much faster. So this is called saltatory conduction, and it's going to happen in myelinated neurons. And so one quick thing about anesthetics, right? Maybe some of you are interested in becoming anesthesiologists. And often when anesthetics are developed, the purpose is to reduce or eliminate the sensation of pain. And so how can you do that? Well, by slowing or stopping the conduction of nerve impulses. And so many of them are going to inhibit the opening of the sodium channels. And so if you inhibit the influx of sodium, well, you're never going to reach the refractory period. And like I said, action potentials are all or nothing. If you don't reach the threshold, if you don't reach threshold, then you are not going to get an action potential. And so, therefore, you are blocking action potentials along sensory neurons. For some anesthetics, like ones that are in dentistry and things, like you still want to be able to move, like with that Novocaine, you should still be able to like move your mouth and swallow and things like that. And so, you don't want to block the motor neurons, you just want to block the sensation of pain. And so these are focused on the sensory neurons. And just like with hypnosis, the idea there is to block your awareness of pain. Like obviously with hypnosis, there's no drugs that are being involved, but you're just trying to change the way that your brain is working in order to block that awareness of pain. Okay, so let's see how much you remember from this little section of video. Our first question: what do we call the local potential that must be reached for an action potential to occur? If you said threshold, you'd be right, and that's typically negative 59 millivolts, but there are many sources that also say negative 55 or negative 60. So 55, negative 65, negative 55 to negative 60 is usually the range that I've seen. Number 2, what happens to the membrane potential during depolarization? Depolarization, break the word apart. Well, our membrane potential during depolarization is going to unseparate. So it's going to move from negative 70 to becoming more positive. So it's going to become more positive. It moves towards 0 and beyond, all the way up to positive 30 millivolts. When won't a membrane respond to any stimulus? No stimulus at all. What's the name of the phase? If you said the absolute refractory period, you'd be right. During the relative refractory period, only very strong stimuli, the ones that are occurring in a very high frequency, those are the only ones that will generate an action potential in a cell that has just conducted a nerve impulse. Number 4, which structures allow saltatory conduction to occur? I'm thinking of 2. There are 2 things that you need in order to have saltatory conduction. All right, the myelin sheath and the nodes of Ranvier. All right, so now that we've gone through how the impulse is conducted through the neuron, the next video is going to talk about what happens at the synapse, what happens in order to get this signal to move from one neuron to the next. But before you move on to that, I just wanted to say, mention one thing. After the refractory period, how is it that the neuron gets back to its resting membrane potential? Well, the way that happens is that during the refractory period, the sodium-potassium pump goes to work. Now, I talked a little bit about the sodium-potassium pump in the first lecture video. And the sodium-potassium pump, it has these channels that are embedded in the neuron cell membrane. And these channels use active transport in order to push the sodium out of the cell and to draw the potassium back into the cell. And when I talked about this in the first video, I was just explaining that this is one way in which the neuron is able to maintain this imbalance of charge, right? And the reason why is because the sodium potassium pump is going to push out 3 sodium ions and only bring in 2 potassium ions. And that's happening at the same time. So 3 out, 2 in. And then another 3 out and another 2 in. But what that means is that it's keeping the inside of the cell negatively charged. It's not bringing in as much positive charge as it is pushing out positive charge. And that's happening at the same time. But what this does is it's going to bring our neuron from our refractory period, from hyperpolarization, back up to a negative 70 millivolts, back up to our resting membrane potential. And so that's how we go back to our salty banana unstable configuration and ready for to accept another nerve impulse to come through. The last thing that I just wanted to mention is that hyperpolarization is usually going to go down to about a negative 80 millivolts. I've seen some sources that say about a negative 90. Whatever the number is, it's below negative 70 millivolts. It's below that resting potential. And then after that hyperpolarization, then you've got our refractory periods happening there as well. But I just wanted to make sure that you knew that during that refractory period, the sodium potassium pump uses ATP to return our neuron to the resting membrane potential state. Thanks.